Okay. So, with that introduction for integral and differential balance equation or macroscopic and microscopic balances, we will begin with the deriving the conservation equation for total mass. So, we are in this part of the course which says total mass balance, conservation equation in terms of integral balance and differential balance, and then we will also look at applications of the integral balance and the differential balance, that is integral total mass balance and differential total mass balance. Okay. So, in terms of outline, we derive the integral total mass balance equation starting from the law of physics and look at applications of integral total mass balance equation, and then derive the differential total mass balance equation and look at applications of differential total mass balance equation. Okay. So, that is the outline under the conservation of mass title. Okay. Okay. After deriving the integral total mass balance equation, we would be taking few applications and solving. What are they? Just to give an idea what is that is in store for us, we will be able to apply the integral total mass balance equation to solve a typical process calculation problem like mass balance over a thickener. Okay. We will be able to apply the integral mass balance equation for flow over a pipe junction and find out, let us say, one of the velocities or one of the flows, and then we will also be able to apply for flow between the parallel plates and find out how the maximum velocity is related to the inlet velocity, and then under a transient condition we will be able to find out how does the density vary as a function of time in a tank through which the air escapes. Okay. These are the kind of applications which you would be able to solve at the end of this integral total mass balance equation. Okay. So, the control volumes are now around the entire pipe here and entire tank here, as we have seen in the previous slide. Okay. Okay. So, let us start deriving the integral total mass balance equation. The starting point for any derivation is the law of physics, and we said that is one of the major objectives of this course, that to relate the law of physics to the conservation equation. The very first statement is the law of physics. What is the law of physics now? Law of physics for a system which states that mass of a system is constant. What is, just to recollect this example which I have discussed a few classes earlier, we had a fire extinguisher and then at time t equal to 0, let us say CO2 is gas inside carbon dioxide. I identify the gas inside the cylinder at time t equal to 0 as my system. Sometime later, if I open the valve and part of the gas escapes the cylinder, still my system is constituted by whatever gas outside and whatever remaining gas inside. Control volume still remains my cylinder, but system has partly moved out of this control volume. So, we said system is made of specific fluid particles, and so by this definition, the way in which I defined a system, mass, let us say here initially you have 10 kgs, let us say 2 kgs have escaped, remaining 8 kg, but still mass of the system is 10 kg. So, mass of a system is constant. Now, we like to write this in terms of a rate of change. So, rate of change of mass of a system equal to 0, mass is constant. So, the rate of change of mass with respect to time that is equal to 0. Okay. Now, these are the statements. Let us see how do we go ahead deriving the equation from this. Okay. Now, while deriving the Reynolds transport theorem, we introduced an extensive property capital B, introduced intensive property small b. Okay. How did we relate that? We related the capital B for a system in terms of this integral and the which is rho b and then dv, and the rate of change of the property can be expressed in terms of this we substitute B in terms of the integral can be expressed in terms of this expression d by dt of integral rho b dv. So, this we have come across when we derived the Reynolds transport theorem. Now, for the present case B system is the mass of the system, okay. And so, the intensive property small b is mass per unit mass, which becomes unity. Okay. So, just to repeat, this is the general equation which is for any property B. Right now we are focusing on the total mass. So, B for us right now is total mass, and this B is mass per unit mass, hence becomes unity. Okay. Let us see how do we write for mass of a system. Okay. How do we write this? What do? We take our system, split into smaller and smaller volumes of delta V I, and each volume has its own density rho I. Earlier we had here B, now which was property per unit mass, presently it is just unity, that is why I have used here 1 here, okay. And now I sum over all the smaller volumes, okay, sum over all the smaller volumes, and now I want to represent this as an integral. So, I consider very small volumes, really infinite of them, and as you the number of volumes becomes larger and larger, the volume of each element becomes smaller, tends to 0. So, I evaluate this sum in the limit of each volume tending to 0, okay, which then you can represent the sum as this integral rho dV. Once again this 1 indicates that B is equal to 1 for this particular case. Okay. So, mass of the system has been represented as integral rho dV. How do you interpret this? Small volumes of delta V I multiplied by rho I, and then all you consider many such small volumes and infinite number of elements, the summation becomes integral, and that is why M system is integral rho dV. Okay. So, when you look at rho dV, the way you should interpret this in terms of this splitting into smaller elements and then summing up all the masses of each of the elements. Okay. Now, let us write this expression, this equation for the case of let us write this expression for the case of mass of a system. What we have done here is we are writing this equation for mass of a system, rate of change of mass of a system. M system has been written in terms of this integral expression rho dV. Now, from the law of physics we know that rate of change of mass of a system is equal to 0. So, this equal to 0 comes from the law of physics. The left hand side just tells you rate of change of mass of a system. This tells you same thing, but in terms of the integral expression for M system. Now, when you equate this to 0, you are invoking the law of physics that the rate of change of mass of a system is equal to 0. So, this is the statement of this. Here we have written the law of physics as a let us say an English statement. This is a mathematical representation of the English statement made in the first bullet. Okay. We say rate of change of mass of system equal to 0, which has been represented in terms of equation in the last line. Okay. So, we have written the earlier step again, rate of change of mass of a system is equal to 0. Now, to be more precise, we are given a subscript saying it is for a system. Okay. Now, what we will do now is use the Reynolds transport theorem, because Reynolds transport theorem relates the rate of change of property for a system to the rate of change of property for a control volume. So, let us write the general form of the Reynolds transport theorem for applicable for any property. Just to recall, this first term of the left hand side term represents rate of change of property for system, right hand side rate of change of property for the control volume, and then this last term, the second term on the right hand side, tells you the net rate at which the property is leaving the control surface. Okay. Now, as we are discussing, the intensive property is B is mass per unit mass, which is unity, and so we substitute B equal to 1 in the Reynolds transport theorem, and then get a Reynolds transport theorem applicable for mass. So, how do you read this equation? Now, rate of change of mass for the system, that is the left hand side term, right hand side first term rate of change of mass for the control volume, then the second term on the right hand side tells you net rate at which mass leaves the control surface. Okay. Now, becomes little more meaningful. Earlier we are using the term, earlier we are using the word property, now that property is mass. So, we can read out this equation in terms of mass. Okay. So, of course, Reynolds transport theorem relates rate of change of property for the system to the rate of change of property for the control volume, in this case mass. So, rate of change of property for the rate of change of mass for the system to the rate of change of mass for the control volume and net rate at which mass leaves the control surface. Now, what do we do? The left hand, this is the equation which is the which came from the law of physics. The left hand side can now be represented using the Reynolds transport theorem, and that is what I have done here. What is that I have done here? I have taken this equation on the left hand side of this equation. I substituted the Reynolds transport theorem from here and completed the expression for the this equation. So, just want to emphasize that this is the law of physics, this first equation is law of physics. The left hand side is in terms of system that has been represented in terms of the control volume and control surface, that is the idea of using Reynolds transport theorem. In the law of physics, in the left hand side I use Reynolds transport theorem, and then so when I do that, the left hand side terms are in terms of control volume, control surface. Of course, yet the right hand side term is still in terms of 0 for system. Okay. But what is the main thing we achieved here? This integral which was in terms of system has been represented in terms of integral over control volume and integral over control surface using the Reynolds transport theorem. Okay. Okay. Remember, Reynolds transport theorem tells you how to replace this integral in terms of control volume, control surface. This equation does not come from Reynolds transport theorem. That statement comes from the law of physics. Using Reynolds transport theorem, you are able to relate integral over control volume, control surface to, right now it is 0 for the system. Let us see how do we represent that also for control volume. Okay. Unless all the integrals are in terms of control volume, control surface, we will not be able to apply for solving or deriving solving a control mass balance problem. Okay. Okay, let us see how do we do that. Okay. So, the stage we are in is that we have written the law of physics, used the Reynolds transport theorem and obtained this equation. In this equation, the left hand side expressions are what we wanted, meaning they are in terms of control volume, control surface, but the right hand side is says that 0 for the system, that has to be expressed in terms of control volume. Okay. Now, to recall back, when we derived the Reynolds transport theorem both for the special case and general case, at any time t we took the control volume and the system to be coincident at any time t, fixed control surface and system boundary at time t. We wrote B system t is equal to B control volume t. So, now that is what is shown here. This is our control volume. We could have chosen a system which is partly outside and partly entering. We could choose a system which is just coinciding with the control volume, or which is just leaving the control volume. Three possibilities are there, several possibilities, but what is the possibility which is most convenient to us? This possibility where the system and control volume coincide, so that the boundary of the system and the boundary of the control volume both coincide each other. So, system gets well defined, much more well defined. So, in terms of our the animation which you have seen earlier. So, these are different possibilities for the system. So, we consider the system which is coinciding at time t. Okay. Yeah, at that point we consider the system to be coinciding with the control volume at time t. What is the implication of that? This 0 for system can be replaced with 0 for the control volume. Okay. Left hand side is what we want. In the right hand side we replace 0 with control volume. Okay. Of course, later on when you start writing, we usually do not write this control volume, it is implied that is for control volume, but at this stage when we go from system to control volume, we should understand how do we really go from 0 for system to 0 for a control volume. Okay. This comes from the law of physics saying that the rate of change of mass is 0 for the system, and now both are coinciding. So, I replace 0 for system with 0 for control volume. So, now this equation is the integral form of the total mass balance equation, okay, where all the terms are in terms of control volume and control surfaces. Okay. Now, of course, in terms of significance, this term, the first term on the left hand side represents rate of change of mass within the control volume. This tells you net rate of mass leaving the control surface, and of course, right hand side is 0. Okay. Okay. So, as I told you, we write the conservation integral form of mass balance equation. We do not specify control volume on the right hand side, it is understood. Now, we have seen that this V dot n automatically takes care of outflow and then inflow, okay, and V dot n is positive for outflow. Just to recall, and the same diagram is shown here, and the n represents the outward normal. So, always the normal is drawn outside of the control volume. So, let us say with respect to this physical geometry, if these are inflows and these are outflows, for this phase the outward normal is drawn in this direction, and this inflow outward normal is drawn in this direction, is drawn in this direction. So, in both the cases, both outlet and inlet, the normal always points away from the control volume. So, outward normal here and outward normal here. Okay. So, this is the outward normal, and in terms of the angle between the velocity vector and the n vector, for outflow you have less than, that angle is less than 90 degrees, and then the V dot n is positive for outflow, and for the case of inflow the outward normal is shown here, and these are the extended inflow velocity vectors. The angle between the velocity vector and normal vector is greater than 90 degrees, and hence V dot n is less than 0 for inflow. Okay. So, because of this integral automatically takes care of surfaces where there is outflow and inflow. Because V dot n is positive for outflow, that term tells you the net rate at which mass leaves the control surface. Okay. So, let us put this all this more very formally in terms of significance of this equation. So, the first term represents a rate of change of mass, okay, rate of change of mass. To be more specific, we say time rate of change of mass, and then it is within the control volume. This tells what is happening to the mass as a function of time within the control volume. Okay. Now, what does the second term represent? It tells you, as we have discussed now, net rate of flow of mass out, okay, through the control surface. Remember, all these are whatever flows in and out etc. through the control surface. All these are parts of the control surface through which there is inflow or outflow. Of course, we already discussed that wherever there is no inflow outflow, the velocity is 0 and this integral will not contribute. Okay. So, that is why it says net rate of flow of mass out through the control surface. When I say through the control surface, wherever you have inflow and outflow, all other parts won't contribute. Now, we have a term which is going to play a major role as we go along, by convection. By convection, what do I mean by convection? You have a stream, this you have water entering through this tube, similarly water entering through this tube and water leaving through this tube. Okay. Now, as we have discussed earlier, this stream entering carries mass with it. Okay. Similarly, this stream entering carries mass with it, and this stream carries mass, of course, out of the control volume. All these wherever there is transport of mass by flow, by bulk flow, we call it as convection. Okay. So, this term we will use several times throughout the course. Right now, we are using the context of total mass. We will say later on extend this to, let us say, momentum, energy, species mass, etc., but all are the same physical significance, that whatever flow entering, let us say through inflow and outflow, with them they carry these properties, namely mass, etc. Okay. So, that is why it says net rate, because accounts for positive and negative in terms of outflow and inflow, net rate of flow, mass out through the control surface and by convection. Okay. So, every term has a significance there. Okay. Okay. And of course, right hand side is 0.